Good afternoon, everyone. Myself, Aarthi. I'm currently a PhD student in IIT Bombay. I carried out this work when I was working in Indian Institute of Space Science and Technology, Trivandrum. So my topic is based on gas sensing, and I focused on sensing reducing gases like hydrogen, methane, ammonia, those kind of gases. So what does a gas sensor do? A gas sensor will sense the gas, and there are many types of gas sensors are available in market. So we work with semiconductor based gas sensors and NDIR based gas sensors. Semiconductor based gas sensors have many subcategories like metal oxide gas sensors, and now 2D material 2D materials has emerged as a gas sensor technology is involving now. And here, semiconductor gas sensor is mostly resistive based. When a reducing gas is coming contact with the sensor, a potential difference is felt in the sensor output. So that is the technology we use. So I chose hydrogen, ammonia, and methane for sensing. Like my sensor, I selected palladium selenide, which is a transition metal dichalcogenate, and zinc oxide, which is a metal oxide sensor. I doped these two, and which is reactive more to hydrogen than the ammonia and methane. So a little bit intro of hydrogen gas. Hydrogen gas is colorless, odorless, and tasteless, and it is flammable easily. We can't see hydrogen flame by our naked eye. Through infrared radiation only we can feel the hydrogen is getting flamed. So it is very light, it can disperse easily. It is 14 times lighter than air. And nowadays we can see that many electrical vehicles using hydrogen as the running mechanism for fuel, and in many fuel cells also hydrogen is used, and there is many possibility for hydrogen leakage. And because it is smaller size, and we can virtually see the flame also, right? So one condition is there that acceleration is there, which means we will feel suffocation if we are radiating more to, like, we are exposed more to hydrogen gas. And its low density will give more buoyancy for the hydrogen gas. And we can't, if it is leaking with more pressure, high explosion will happen. So there is a great demand for hydrogen, a good hydrogen sensor, which is selective, sensitive, and which is repeatable. So we are, I started with the transition metal dichalcogenate. Transition metal means we all know that D block metals. Chalcogen family will involve sulfur, selenium, and all. So here I chose palladium and selenium as TMD. And the structure is very interesting. It is layered structure. We all know that 2D layering. And here the dark colored atom, like dark blue color represents the palladium, and the yellow color represents the selenium atoms. And the next diagram is the top view of that. The crystal structure will look like this. So nowadays, the transition metal dichalcogenates are used in various sensors like piezoelectric, acoustic sensors, and photo detectors also. So we can look into the palladium selenide now. The palladium selenide is a palladium atom is bonded with two selenium atom, and the bond angle is given here. And it is having very high photodetective property. And it is difficult to form a monolayer of palladium selenide, and it is having a wide band gap range from bulk to monolayer. So the material we synthesized will be in between this band gap range. So it will fall into the semiconductor. So zinc oxide is a very good metal oxide semiconductor for hydrogen sensing. So it is also sensitive to light. So we thought of incorporating these two by adding a 2% of zinc oxide to the palladium selenide for detecting these reducing gases. So we took 2% of zinc oxide with the palladium selenide, and we dispensed over the platinum IDE. And a very interesting technique we use for the synthesis of palladium selenide and zinc oxide is microwave assisted technique, which means here we did not use any CVD or a high level technique. We use this microwave assisted synthesis, which means we are using microwave radiation to heat the sample. We use a solvent for heating the sample. Here we use ethylene glycol as the solvent, and the reaction is very fast, and we will get less wastage will be there, time saving and energy efficient. And we got very good deals using this microwave assisted synthesis. And this is the synthesis method. We used selenium and sodium sulfate, and we formed a selenium salt. And then we incorporated palladium chloride to that selenium salt, and we kept it in the microwave assisted technique. And finally, we got some byproducts, and we removed that through centrifuge. We washed and filtered, and finally we did annealing and all. So same procedure we followed for zinc oxide synthesis. This is the principle of operation. Actually, we will be coating the sample over the platinum IDE. And we have a cathode and anode tips in the IDE. And we will put synthetic air initially. Synthetic air is a combination of 80% nitrogen and 20% oxygen. So initially, we will be having a conduction from anode to cathode in the IDE, right? So when we are purging the synthetic air over it, the oxygen molecules will take the electrons from the conduction band of the material. So we will get the reduced conduction. And when we are giving the reducing gas like hydrogen, the oxygen molecules will react with the hydrogen and it will leave the electrons back to the material. So we will get the conduction again. This is the resistivity sensing process. And this is the same image we got for palladium. It is like a flake. Palladium selenide flake, and zinc oxide, it will be like a nanosphere. So this is the XRD data. And in the XRD data, it has seen that not only palladium selenide is formed, and some palladium is also there. And zinc oxide and silicon peak is there. It is coated on silicon for that. So how this sensor work means, we had palladium selenide layers. These selenium layers help in the trapping of adsorption of hydrogen gases over its sides. And this palladium acts as a catalyst for breaking these hydrogen molecules to hydrogen HH. And this hydrogen later give electrons to the conduction band of the zinc oxide, which increases the conductivity. So by this technique, we got the sensing of hydrogen. And we got the response of 34%. And the sensor response can be calculated by this formula. Resistance in gas and resistance in air. Gas means the hydrogen, air means synthetic air we used. And this is the response. And see, the other two gases are not at all showing any response compared with hydrogen. We use 10,000 ppm hydrogen gas and 10,000 ppm methane. But methane is not at all showing any conductance. And the rise time is 120 seconds and the fall time is 29 seconds. So our sensor material showed excellent selectivity towards hydrogen compared to other reducing gases. So the further scope is that we will try to incorporate different weight percentage of zinc oxide doping towards this, and I am working in this area now. Thank you.